Let's start first with a brief history lesson with the data encryption standard. DES is a symmetric block cipher developed by IBM in the 70s. At that time, IBM was an unchampioned worldwide leader. IBM research would set the trends for all other competitors in the field. Data encryption standard encrypts 64-bit blocks of data with 8 letters in the ASCII code and a parity bit, using a 56-bit key. How is this possible? After all, you probably remember that it was claimed that DES used 64 bits. That's actually true, but the remaining 16 bits is an earlier checksum. The true entropy is 56 bits in this case. If the key is truly random, it has at best 56 bits of randomness. 56 bits doesn't have quite the same ring to it. It's always better to claim that you use a longer key. This is the source of the misconception that is still popular today. The data encryption standard never used 64-bit keys. The encryption process is made of 26 Feistel rounds, the rounds we mentioned before, and 2 permutations called the initial and final permutations. The initial and final permutations don't contribute in any way to overall ciphertext security, or their contribution is small and insignificant. It's unclear why they were brought in the first place. It's usually assumed that they were introduced to make DES encryption and decryption hardware implemented. The 2 permutations are cost-intensive to an extent. Hardware is able to go through them at a much faster rate than software. Their implementation can be explained simply as a consequence of hardware manufacturers' lobbying. The permutations don't add to the security of a ciphertext in any way. In each round, a half of the round key, 32 bits, is expanded to 48 bits. The result is 2 pieces, 48 bits each. One piece is encrypted using the function f, and the result of this operation is combined using the exclusive disjunction, the XOR operation, with the other half. The function f is, above all, a substitution permutation box. This is the S box you saw earlier. One of the 8 S boxes, each time a different one, is selected to use in a permutation. Why are the S boxes structured in this exact way? What is the basis and source for the values located in the intersections of individual columns? Well, this is also one of the greatest enigmas of the 20th century cryptography. The data encryption standard was developed in the US, where IBM is established. Some people believe that the specific structure of the S boxes has made it possible from the onset for US government agencies to reverse the whole process at a small cost. This has been neither proved nor disproved, and still no one knows on what principle the S boxes were selected. Our S box is a 4x16 table. The values it contains range from 0 to 15. To be able to transpose some data, you only need to locate appropriate table cells. The first and last bits of the encrypted parts of the data are used as row numbers. The remaining bits are used as column numbers. Find the coordinates and look up the content of the S box. On completing all Feistel rounds, you have to perform a final permutation. Just like in the initial permutation, this permutation does not enhance the security of the ciphertext. In retrospect, it seems that the block used by the DES algorithm is too short. While block length does not always correspond to the ciphertext security, blocks that are too short can prove problematic. 64 bits are not really sufficient. The key, meanwhile, is definitely too short. We'll discuss later the reason why the practical security of a system amounts in fact to half a key's size. DES was cracked using the brute force attack in 1999 in less than 24 hours. This attack was proved and deployed by Electronic Frontier Foundation. To build a machine capable of mounting a successful attack, the organization made use of distributed member computers. A large geo cluster was built. Each node was provided with a share of key spaces to test. Together, the cluster was able to crack the DES cipher in 22 hours. DES is vulnerable for purely cryptographic reasons. The first point is that a significant dependence can be observed between round keys and cipher keys. This relationship is evident especially if 0 is the key. Round keys in that case are also 0. Another problem the standard exhibits is the complementation property, which refers to some relationships existing between the key, the plaintext, and the ciphertext itself. If you encrypt all bit complements using key complements, the output is the ciphertext complement. Today, the DES ciphertext can be cracked in a matter of minutes. In 2004, the NIST Institute withdrew the recommendation for the algorithm. The image depicts Copacabana, one of the many internet-available devices for cracking DES in real time.